Hello. In the last two videos, we were um, looking at some of the mathematical aspects that we are going to utilize in this course. Mainly, they covered matrices and quadratic forms. And we saw that if you have two quadratic forms, and one of which is positive definite, then we can put these two quadratic forms as sum of squares, and one of them which corresponds to the positive definite quadratic form, that can not only be put as a sum of squares, but also the coefficients which appear in front of these squares, they can be chosen to be unity. Okay, so that is what we were talking last time, and today we are going to start a new topic which we'll spend some time with, and this is oscillations. Okay, so that's what we are going to do now. So I will start this lecture by defining a natural system. So generally, when we are dealing with problems, it will often happen that we do not need to have time appearing explicitly in the transformations when you go from Cartesian to generalized coordinates. Okay, so the time does not appear explicitly there. That happens very often. Also, the applied forces, the forces that are under your control, not the ones arising due to constraints. The applied forces will be conservative. This also will be a frequent occurrence, and that constraints will also be very often holonomic. Okay, meaning that you will be able to, from the outset, get rid of the degrees of freedom which are not independent. So you'll be able to utilize the equations of constraints and then write down your system only involving independent coordinates. So these three conditions are very frequent, and if a system obeys this, or if a system is obeying this, then you say that the system is a natural system. So let me write down what I have said just now. So a natural system. Okay, and the conditions are the following. A, the or maybe I should write even without this. So what we are saying is, if you look at Q, relation between the Cartesian coordinates and the generalized coordinates, this does not involve time explicitly. Okay, that's one. Second is, forces are conservative. Okay, and third, constraints are holonomic. Okay, if these three conditions are holding true, then we say that the system is a natural system. Okay, and for a natural system, clearly the kinetic energy, which is in general a sum of three terms, one is of degree 0 in generalized velocities, T0, that is what we have been saying. Another is T1, linear in generalized velocities, and T2, quadratic in generalized velocities. But for a natural system, you will have only T2. For a natural system, the kinetic energy contains only T2. Okay, and the Lagrangian will be of the form of the following form. So your L will be, so let me write down explicitly t2, it will be half aij, which in general depends on all the coordinates qi's, which I am denoting them by q, and then you have qi dot qj dot minus the potential energy, which depends on again all the generalized coordinates. Let me put a summation 1 to the total number of degrees of freedom. Okay, that's the definition of a natural system. Now we want to talk about oscillations, and the generic situation is the following. Usually your system would have a equilibrium configuration, meaning if you put your system at rest, so let's say all the generalized velocities are 0, and if you put your system in such a configuration, and if system remains in this configuration, meaning it always all the generalized velocities remain 0 with time, so they do not change, they keep remain 0, then you say that the system is in is in an equilibrium configuration. I mean, the configuration may be stable or unstable, but that's what you expect, that your system is not going to move away from it if that is an equilibrium configuration. Okay, so let me write this down. EQ BRIUM. So what I'm saying is, let's start with all the generalized velocities qi, all of them are 0 for all I. Qi dot, okay, generalized velocities, they're all 0. And if, so that's how you start, and if qi dots remain 0 at any other time, so let's say this you have started at t equal to 0. So at t equal to 0, you have put the system in such a form that all the generalized velocities are 0. And if at any later time this still remains true, then it means that your system is residing at an equilibrium point. Okay, for any t greater than 0, then we say then the system is in equilibrium. Let's take a very familiar example. Let's say I have a pendulum, okay, and your generalized coordinate is theta in this case, right? Now if you take this mass and put it here vertically downwards and put it at rest, then it will remain there, it will not move, right? So at any later time t, it will still be lying there, but if you give it some velocity there at the lowest position, then of course it's not going to stay there. So clearly you see that this point will be an equilibrium point because this condition is holding true. Okay, so that's good. Now we need to find out the condition for equilibrium. So this is what we expect for, I mean, this is the definition for the system being in equilibrium, but what else needs to be satisfied for this to hold true? That's what we want to look at. So we start by looking at Euler Lagrange equation, because that is what tells you how the system is going to evolve with time. So Euler Lagrange equation for a natural system is d over dt. Here you have generally del L over del Q dot, but L has a U, and that u does not depend on generalized velocities. Okay, that's the part of definition of a natural system. So I have only the kinetic energy term here, q I dot. Okay, and then I have just split the L into T and U and written down like this. Right, that's your Euler Lagrange equation. If you combine these two, this becomes del L over del Qi. Okay. Now let's look at this thing. Let's see what del T over del Q I dot is. So this piece, this will be just A I K Q K dot. Okay, what I've done is taken this one, this piece, and have differentiated it with Q with the generalized velocity Qi dot. So that's what you get. Also, let's see what del T over del Qi is. Now I'm looking at this one. First I had looked at this one, this piece. Now I'm looking at this one. Now this is del T over del Qi. So the Q dependence is only in A. These are the velocities. So if I take a derivative, I get, you have a half del A I, let me put J, in fact I should put, yeah, J and K. Okay, I've changed the indices because they are dummy, and del Qi, that's fine, this piece, and it's contracted with Qj dot Qk dot, right? Okay. Now clearly, if I put Qk dot for all times to be 0, okay, then both these terms are going to vanish. So if Qk dot is equal to 0, all t, and k is not just one particular but all the coordinates, so k runs from 1 to n. Okay, then your this piece and this piece, they are both 0, right? So del T over del Qi dot is 0 for all times, and del T over del Qi is also 0, which means that this piece is gone and that piece is gone. Now this entire equation will be satisfied. Okay, it has to be it will get satisfied only if del U over del Q, that also is 0. Otherwise, this will not be satisfied, right? Which implies that the system to be in an equilibrium configuration, we had the condition that del U over del Qi is 0. Okay, that's the condition we get. Which means we need to look at the function u and search at which point q is q1, q2 and all, okay, at what point that derivative is 0, and that point will be called an equilibrium point. And clearly this is a point of extremum where the potential will take its either maximum or minimum value. Okay, so as I said, I'm not sure what I said, but there are two things which can happen. Whatever point q0 you get from here, okay, where this condition is satisfied, this q0 could be either a stable equilibrium or an unstable equilibrium. And what do I mean by that? I mean by that the following. So it may happen that you put your system at the equilibrium place where this condition del u over del q is 0, okay, and if you put it there at rest, it remains there forever, okay, that's fine. But let's say you displace your system from that position by an infinitesimal amount, okay, a little bit. Now if you do so, there are two possibilities which can happen. One is that the system moves away from it a bit, but it tries to come back, okay, so it remains in the vicinity of that point q naught. It doesn't go away from there, so it remains in the neighborhood of that point q naught. If that is the case, your equilibrium configuration is a stable configuration, okay, it's stable, it remains there, your system remains there. But it may also happen that even though you can place a system there at rest, but if you give a small infinitesimal nudge to the system which takes it away from that point, system does not come back to this place, so it goes further away, okay, it doesn't want to return there. For example, you can, a very simple example could be, think of a sphere. If you put the ball on the top, take a ball and put on the top, if you leave it at the rest there, it will remain there. But if you give it a slight displacement, it's not going to come back. But if you take a bowl and then you put the thing at the equilibrium place at the center, if you leave it, it remains there. But if you take it away from there, it remains in the vicinity of that point, okay, it doesn't go away far. So that is what generally stable and unstable equilibrium are. Maybe I should write that down. What happened? Yeah. Stable equilibrium. Okay. And infinitesimal displacement away from q0 produces a motion that keeps it in the vicinity, okay, in the vicinity of q naught. And clearly, if you have unstable, it will take it away from q naught. It doesn't return back. Okay, it just goes further away. And depending on what is happening further away from that point q naught, your system may keep going away forever, or let's say it has another maximum minimum, so it can do something else. But as far as the neighborhood of point q naught is concerned, these are the statements that we can make. Now, of course, we are going to be interested in stable equilibrium. Okay, so henceforth I will talk only about stable equilibrium. Stable equilibrium. Now what I can do is, without loss of any generality, I can choose that point where you have the equilibrium, the stable equilibrium, as to be the origin of your coordinate system. So I say that all the q's are 0 there. That's basically choosing the origin of your coordinate system. Okay, so that's what I'm going to do. So without loss of generality, I can set q naught to be 0, okay, which basically means that I'm saying qi, let's say, how do I put it, qi, okay, qi0 equal to 0 for all I. Okay, here Q naught stands for the entire set of coordinates. That is good. Now I'm going to be interested in small displacement around Q naught. You see, if your displacement is large, then just knowing about the potential in the vicinity of Q naught is not sufficient, right? Then what is happening globally will determine the motion. For example, if there is another minimum somewhere, and if you displace it by a large amount, your system may end up in this other minimum. Okay, so we are interested in small displacements. And if I'm looking at small displacements, what I can do is I can take the potential and do a Taylor expansion around this point Q naught, which I call the origin now. Okay, because I have set that already to 0. So I will do a Taylor expansion for small displacements. Okay, I'll do a Taylor expansion. So U of Q is U of 0. So I'm expanding around the point 0 plus del U over del Q K evaluated at the origin QK. That's the displacement from the origin. QK is now displacement from the origin. Okay, so that's one advantage of putting everything at origin, so I don't have to write QK minus something, plus half, you should take a second derivative of U with respect to Q J Q K, and again this thing should be evaluated at the origin. So these two numbers are now these two quantities are numbers. They are not functions of Q's anymore. They are just some numbers which are determined by your system. Okay, and then you have Q J Q K, plus you'll have all other terms. So I will write them as order Q cube. Let me just put cube. Okay, so I'm by this symbol I mean I'm dropping, all these terms which I am not showing, they are all order cube or higher. Okay, depending on the system, some of the terms may vanish also, some of the orders may be absent, but generically this is what the statement would be. Okay, now I can do another thing. I can set U of 0 to be 0. See, potential, you can, the absolute value of potentials are not important, that you, I believe, already know. It's only the relative differences which are important. So I can set that the potential energy of the system is 0 when it is at the equilibrium configuration. So that choice I can make. So let me make that choice, and I set this to be 0. Also, because I am saying that my system is in equilibrium, I have already seen that that translates to saying that the first order derivative of U vanishes, right? That's what we have seen a couple of minutes ago. So I put this to be 0. See, this follows from our requirement of equilibrium, and this is a choice I have made. You are free not to choose this. You may keep it something else, non-zero. Nothing will change, right? But anyway, things look simpler if I make this choice, and with this choice I am left with this term which is quadratic in Q and higher order terms. So with that I get U of Q. I will write this as, I believe, yeah, I think it will be half. This I call U J K. So these are just numbers. QK, QJ, QK plus higher order terms, which I am denoting by order Q cube. Okay. Now clearly the matrix elements UJK. So you can think of as a n cross n matrix, right? See, if you look at J and K, they run from 1 to n. That's the number of degrees of freedom you have. So this UJK, if you look at them, these are n square numbers, total n square in number, and they form a matrix. And the matrix we call U, whose entries are this U11 and so forth. Okay, U12, etc. And clearly the matrix is symmetric because of this definition of it. If you interchange the two derivatives, it doesn't change because these derivatives differentiations commute. Okay, so U is a symmetric matrix. Is a symmetric matrix, real symmetric matrix. Okay, that's good. Now let's look at the kinetic energy term. Before I do that, okay, that's fine. Now I look at, okay, maybe I should write it down. UJK is symmetric because del Qj del Qk, this order does not matter. Okay, that's good. Now let's look at the kinetic term. And what did we have? We had T equals half, and you had a summation over I and j. Aij, it depends on Q's in general, and Qi dot, Qj dot, that's the form for a natural system, as we said. Now what I'm going to do is I'm going to again do a Taylor expansion around origin where your system is in equilibrium. Okay, so I write it as Aij Q equals Aij of 0 plus over delta Qk evaluated at the origin, Qk plus higher order terms. Okay, so all the terms will be there. That is good. Now, okay, that's fine. Now let's look at our Euler Lagrange equations of motion. So Lagrangian is there, but I want to also look at the equations of motion, and my intention is to see how much of this expansion, okay, so up to what order I should keep both in the kinetic energy and the potential energy terms, so that my equations of motion are linear. Okay, so I'm going to be I'm interested in looking at the system in a linear approximation, and the reason being that I can solve it without running into any complications. That system I will be able to solve. So I want to see up to what order I should keep terms in T, and up to what orders I should keep terms in U, so that my equations of motion are linear. Okay, that's what I want to do. And clearly, if I do so, it will not describe the true motion of my system, but it will capture the most general features, hopefully, if I remain in the vicinity of the equilibrium position. Okay, so that's what we want to do, and that's what we are going to do now. So let's look at equations of motion. So we are interested in looking at at linear approximation of equations of motion. Okay, maybe I should just tell you. I'll just okay, I will leave it as an exercise. I do not wish to do that simple steps here. So exercise, show that if you retain or if you approximate, let's say if you approximate the potential energy to the following, where was it? Here. If you keep only this term and drop all other terms which are here, okay, so half uij qi qj and drop all other terms in potential energy, and if you take T to be just this first piece, okay, so I put half aij and qi dot qj dot. If you do so and throw all these terms, okay, then your equations of motion that you are going to get for this system will be linear, okay, and that's not difficult to check, so I will encourage you to do so. So under linear approximation, I would before writing that, I would write, instead of aij, I will write half tij. Okay, so this matrix made by these elements aij 0, these numbers, I will just denote by tij so that it sounds a bit like kinetic energy matrix, or sounds like kinetic energy matrix. Okay, so under linear approximation, any system, say I'm not making any assumptions about the system, any system you can approximate its Lagrangian by this, which is nice. This summation over I and j is implied. Qj dot t minus u, so you have half uij qi qj, and I have dropped all the other terms. Let me put summation over I and j. That's nice. So this will be our starting point for analyzing any system near its equilibrium configuration. And let me just mention that your T ij, this is symmetric matrix, your U symmetric, okay, and yes, so next time we will start looking at this system, but now you can already try to bring in what we were talking about in the last two videos where we were talking about some mathematics. You see, what you have in front of you is a quadratic form here and another quadratic form here. Okay, so we will ask in the next video whether these quadratic forms are positive definite, positive semi-definite. These things we are going to ask, and if we were lucky, and if we are lucky and we figure out that maybe one of them is positive definite, then we will do what we learned last time. We will put them in diagonal form, okay, and then you'll see some very nice results come out. Okay, that will be the goal for the next video, and we'll stop this lecture here. So see you then in the next lecture.